Hello all, welcome to Datafuse Analytics. In the last session, we studied the entire theoretical part of Variational Autoencoders. In this particular session, we will be implementing Variational Autoencoders in Python right from scratch. So let's start the implementation by importing few packages. I'll be implementing this in Google Colab. Let me connect to this runtime first. We need GPU to train this particular model. So we will need one GPU. So T4 GPU is available. I'll just save it and let's connect it. So we will require NumPy. We will also require matplotlib. Then we require TensorFlow. Then we require TensorFlow.Keras backend. Then we require SciPy. Then we require few packages from few modules from TensorFlow.Keras. The first we need is layers, then datasets, then models. Also we will require callbacks, then losses. We require optimizers, metrics. I think these packages will do for now. Let's solve this error. This should be from. Okay, now all these packages are imported. Now we will require helper functions to display images. For that we will refer to the previous script that we used for vanilla autoencoders. So I'll give you this link. You can copy paste this entire two functions from here. So these are the helper functions. To display images, and it will require this matplotlib, and I am just copying pasting it here. Okay, so these are this is our helper functions. Now let's focus on preparing data. Now for this implementation, we will be using the same fashion MNIST dataset. This fashion MNIST dataset is a collection of grayscale images of clothing items, and each image is of size 28 x 28 pixels, or resolution of each image is 28 x 28. So let's import xtrain, then we have ytrain. I'm using the same syntax like we did in the first implementation of this vanilla autoencoders. So if you have not gone through that implementation session, I'll provide that link. And this entire code I'll make sure to upload in my GitHub repository. So let's run this. If you are running it for first time, it will download from the internet. If I try to run this multiple times, then it won't re-download it. It will store it in your cache memory. Now these images, they are obviously of 28 x 28 pixels, and each pixel value ranges from 0 to 255. Now to make them suitable for our network, we need to pre-process these images. Now we will pre-process these images by scaling the pixel values between 0 and 1. Now additionally we will pad the images to a size 32 cross 32 to simplify how we work with this data and how this data will pass on through the network that we are dealing today. So let's pre-process this data. Let's write a function, or you can straight away take the function from here in the previous session of Vanilla Autoencoders. Let's run this block of code. Then we have xtrain here. Then we have xtest here. We will call this function preprocess images, and as an input we will give xtrain. Here I'll again call preprocess images, and again I'll give xtest as input. Now let's try to display few images. So we will call this function display images, and in input we will give xtrain. Okay, so this is our training data. If you want to see few images from testing set, that we also can show. So these are few of the images from testing data. Now let's do the actual work of building variational autoencoder. So let's build variational autoencoder. Now first we need to create a new sampling layer. So class sampling layers.layer. Now this sampling layer is used for sampling from the distribution which is defined by Z mean and Z log variance, which we already saw in the previous session of theoretical variational autoencoders. So now we will create a new layer by subclassing the Keras base layer. So directly we will define this def call self and then inputs. Now we will use the reparameterization trick which we saw in the last session. Now this reparameterization trick is used to build a sample from normal distribution which is parameterized by Z mean and Z logarithmic variance. So Z mean comma Z log variance equal to, let's say, inputs. Then we have batch equals tf dot shape Z mean of 0. It has to be like this. Then this dimensionality equal to tf dot shape Z mean of first element. Then we have epsilon, which is equal to k dot random normal shape will be equal to batch comma this dimensionality which we computed here in the previous step. Then we need to return Z mean plus tf dot exp 0.5 into Z log variance and then multiplied by epsilon. So these are all the formulas which we studied in the last session. So if you are not aware of this, I strongly recommend you to go through the theoretical variational autoencoders video and then you implement it. So even if the code is available in GitHub repository, I strongly recommend you to first write the code if you are learning, and then you can copy paste it if you know how to implement it. So let's define few parameters. Let's say image size will be 32 and embedding dimensions will be 2. So these embedding dimensions I'm keeping the same as we kept during the implementation of vanilla autoencoders. So now let's design the encoder part, right? Let's say the input to encoder, that is encoder input layer, will be layers dot input. Here shape will be equal to that 32 comma 32 comma 1. So here 32 is our image size, so I'll just copy paste this variable 32 comma 32 comma 1. 1 means number of channels. Then let's name this layer. I'll give this name as encoder underscore input layer. Let's say input layer. Okay, now we will stack few convolutional layers. So there will be 3 convolutional layers. So layers dot conv 2d 32 comma 3 comma 3. Then stride will be equal to 2. We will use activation as ReLU, rectified linear unit, and we will keep padding as same, and input to this layer will be the previous layer's output. So encoding underscore input. Okay, now let's design second convolutional layer. So I'll just copy paste it again, x equals to this, and we just need to change few parameters. Instead of 32, now we will have 64. Everything will be same except here. Now the input will be this x. Now let's design third convolutional layer. Again x equal to this. I'll just paste it. Instead of 64, it will be 128, and everything will be same now. Okay, so this is our stack of convolutional layers. So we have used 3 convolutional layers in total. Now let's define a variable, that is shape before flattening. This we will require further during the designing of decoder part. So k dot int underscore shape of x. Okay, now I'll just comment is like decoder will need this. Then we have x equal to, we'll just flatten the output of previous layer. So flatten, so that it can be inputted to the next dense layer. Okay, so now instead of connecting this flattened layer directly to the 2D latent space, we will connect it to layers zmin and z logarithmic variance. So zmin equal to layers dot dense. We will have embed dimension here. Embed dimension means 2. Then we will just write this name of this layer. Let's say this is zmin layer, and input will be x. Okay, then let's define z logarithmic of variance, which will be equal to layers dot dense embed dimensionality. Again we will name this layer. Let's name this as z log variance layer, and input will be x. Okay, now the next will be the sampling layer. Now this sampling layer samples a point z in the latent space from the normal distribution, which is defined by parameters z mean and z logarithmic variance. So z equal to sampling say z mean comma z logarithmic variance. and this sampling functionality we already wrote above here. Then we will write encoder equal to models.model. Now this is the Keras model that will define this encoder. Now what is this encoder? It is simply a model which takes an input and outputs z mean and z log variance, and also a sample point z from normal distribution, which is defined by these two parameters, z mean and z log variance. So here encoder input, then we have z mean, we have z log variance, we have z, and let's name this layer. Name is encoder. We will simply print encoder.summary just to understand how much there are trainable parameters and what is the entire architecture of this encoder. Let's run this block of code. We are getting this error, this convolutional 2D is not defined here. Okay, so we have to write layers dot convolutional 2D, layers dot, again here layers and then dot. Let's run. Again we have got this error, keyword argument not understood stride in this first. Okay, instead of stride, this is the actual parameter, strides. Again we will rerun this block of code. Then we are getting another error, that is encoding input is not defined. Oh sorry, this is encoder input, not encoding input. So this is the fun, guys. If you actually code it right from scratch, then the fun which you get in solving those errors, that is like incomparable if you copy paste it from somewhere and then just run this. So I strongly recommend you to write the entire code. Even if you have the code ready, write it by yourself in the first time, and then in future if you want to refer it, then you can copy paste. So this is the entire architecture, the summary of encoder. The total parameters are this month's, about 1 million, and trainable parameters are the same and non-trainable parameters are 0. Now let's design the decoder. Let's say decoder input, it will be layers.input layer, then shape will be equal to the dimensionality of embedding, so embed dimension, which is 2. Then we have to keep a name to this layer, let's say decoder input layer. Okay, now we will format this. Now we have to format the input layers, so let's say layers dot dense np dot prod. Now we will use here shape before flattening, this variable which we kept it for future use, this one. Okay, and input will be decoder input. Then we will reshape this, so x equal to layers dot reshape, that will be shape before flattening, and then x. Now here x will be equal to layers dot conf 2d and transpose. Now why transpose? Because we need to generate images, and that's why we'll be using this transpose. So in this transpose, the first argument will be 128, then 3 comma 3, then we will keep strides as 2. So we will be stacking up now convolutional layer. So instead of simple convolutional layers, we will be stacking up convolutional 2D transpose layers, so that we can upsample the images from that two-dimensional input of which the decoder gets. We will keep activation as ReLU and padding will be same. Input will be X. Let's define second convolutional layer, convolutional 2D transpose layer here. Okay, now instead of 128 we will write here 64. So it is a mirror image of encoder. The only difference is we are using convolutional 2D transpose, and in encoder we use simple convolutional 2D. Now let's define the third layer. Instead of 64 we have to write 32 and everything will be same. So these are our 3 convolutional 2D transpose layers. Now decoder output, which will be equal to layers dot con2D. First argument will be 1, then 3 comma 3, then strides will be equal to 1, activation will be equal to sigmoid, padding we will keep as same, and let's name this decoder layer. So name will be decoder output layer, and input will be the previous, that is X. Now similarly we will write here decoder equal to models dot model decoder input and decoder output, and we will just print decoder dot summary. Let's run this block of code. And now it executed without any error, and this is the summary of decoder. Now the total training parameters is about 2 million, that is 2.4 million, 24 lakhs. Not 24 lakhs, it is just 2,46,000, sorry. And the total trainable parameters for encoder was about 1 lakh and not 1 million. So sorry for that goof up. It is just 1 lakh and it is 2.4 lakh for decoder. Now that we have successfully defined encoder and decoder layer for our variational autoencoder, let's train our variational autoencoder. The next step is let's train our VAE. Now in order to create this VAE model, what we will do is we will just extend this Keras model class, enabling us to incorporate KL divergence calculation into custom train step. Now as we saw in the theoretical session that in order to train variational autoencoder we need 2 types of losses. The first is the reconstruction loss and second is this KL divergence loss. Now in order to incorporate this KL divergence loss, we need to extend this Keras model class. And how to extend this Keras model class, that I am showing here. So what I have done is I have defined another class and named it as VAE. Obviously it states variational autoencoder, and then I'll use this models.model of Keras class, Keras model class. We will have encoder, we will have decoder, and few variable argument, that is kwargs. Then we will use super keyword here, self, and then init, and then kwargs. Then self dot encoder equal to encoder, self dot self dot decoder equal to decoder. Then we have self dot total loss. So total loss, we have total loss tracker, which will be equal to matrix dot mean, and we will name this layer as mean equal to total loss. Then we have reconstruction loss. Again we have this tracker for that, and matrix dot mean, and we will name it as reconstruction loss, and the final loss will be KL divergence. So KL loss tracker equal to, again the same, matrix dot mean, and name equal to KL loss. KL loss. Okay. So that's it with this init functionality. Then we will use this property decorator to define this metrics functionality, which will return a list of, first it will return total loss tracker, then it will return reconstruction loss tracker, and finally it will return, yeah, you guessed it right, KL loss tracker. Now we have to define a call functionality. In that, the first will be self and then inputs. So here we will have z mean, z logarithm of variance, and the final, that is z, which is sampled from the standard distribution, and we will have encoder and inputs. Then reconstruction will be decoder. The input to this decoder is z, and then we will return z mean, z logarithmic variance, and then reconstruction, or the output from decoder. Now let's write actual train step. So this is the custom train step that we are writing. How cool is this? Like, we are actually writing our own training step. But before that, let me introduce you to one new concept, which is called as TF dot, that is TensorFlow dot gradient tape. So we will be writing entire functionality of training step within this loop. Now this TensorFlow's gradient tape helps to calculate gradients during a forward pass. Now in order to use it, we just need to wrap the entire code that performs the operation that we want to differentiate with this tf.gradient tape context. So here we will be writing a statements, or we will be wrapping our entire code within this tf.gradient tape. Now after recording the operations, we can compute the gradient of the loss function concerning certain variables using tape.gradient and these gradients are then used to update the variables with optimizer. So let's write the entire code. So z mean z log variance and reconstruction tf dot reconstruction equal to self data. Then we will set beta, a parameter, as let's say 500. Then reconstruction loss will be equal to, we need to reduce this loss, like, so tf dot reduce mean. Then we will write the entire formula for this reconstruction loss. So beta into losses dot binary cross entropy. Then in this, first it will be data, and the second parameter it will be reconstruction, that is the output from decoder, and finally we need to specify axis. So here the axis will be 1, 2, 3. So this is the reconstruction loss. Now let's define KL divergence loss. So KL loss equal to, again, tf dot reduce mean, and in this we need to write the entire functionality or the entire formula for this KL divergence. So tf dot reduce sum in this minus 0.5 into 1 plus z log variance minus tf dot square z mean minus tf dot exp z log variance. So this formula I have already studied during the theoretical session. So I am repeatedly referring to the previous session, the theoretical session, so that you can implement with understanding what is going on. And then we will have this total loss, which is nothing but summation of reconstruction loss and this KL loss. Okay, so this is our train step. Now let's come out of this gradient tape and let's define this grades as tape dot gradient total loss, comma, self dot trainable weights. It should be self. Now we need to define an optimizer. So self dot optimizer dot apply gradients. In this we will have to zip these grads and trainable weights. Then we will have a total loss tracker. We need to update this by using this update state functionality with this total loss. Again we will get this reconstruction loss tracker dot update state and we need to update this with reconstruction loss. Then we have self.kl loss tracker. We need to update with KL loss, and then finally we need to return dot name and then result for m in self dot metrics. So this is the entire functionality for training step. Now let's define a test step as well. So the definition of test step. It is TAPS. I'll just rewrite it tape. So there might be few errors coming up if we actually run this code, and we can solve this one by one. No worries in that, but let's complete this code. So in order to write this test step, the input will be data, and if is instance, if the data type is tuple, then data will be data of 0. Now z mean z log variance and z reconstruction will be equal to self of data. Then we need to specify the reconstruction loss and KL divergence loss. So we can actually copy paste it from the training step, from this beta to this total loss. I'll just paste it here, and we can return the total loss, that is in form of loss. Then we can return reconstruction loss and finally the KL loss, Kullback Leber divergence loss. So that's it. So now we have defined training step as well as test step. Now let's run this block of code. We are getting this error, return m name. Okay, let's solve this. Okay, it should be a dictionary instead of. Okay, let's run. Okay, unexpected indent. Let's fix this error. Got it. It should be here. Okay, let's run. Okay, we have successfully executed this block of code. Now let's define this VAE equal to VAE, the object of this class, and input will be encoder and decoder. Now finally guys, we can start training. Okay, let's solve this error. Apologies for my excitement, but let's first solve this error. Local variable metrics referenced before assignment. Okay, so one major mistake that I have done is I have defined all the functions within this init. That should not be the case, right? So I'm removing this outside the init. I think that will work now. Let's rerun this. Okay, everything is working now. Let's try to start the training. Let's start the training. In order to start the training, we need to compile the variational autoencoder. So we need optimizer, which will be equal to optimizers dot addm. In this we need to specify the learning rate. So LEAR learning rate, which will be equal to I'll keep it 0. Let's say 0005, and then VAE dot compile. In this, the optimizer will be this optimizer. Okay. Now let's create a model and then save the checkpoint. So model checkpoint callback. So we will use callbacks module, callback dot model checkpoint. In this we need to specify the file path. So file path will be, let's say, checkpoint. We need to give few arguments like save weights, save weights only, which will be keeping as false. Save frequency, FREQ. We will be saving each and every epoch, and then monitor will be as per loss, mode will be minimum, and save best checkpoint only we will keep as true, else it will occupy lots of memory space, and verbose will be 0. Let's define let's run this, and let's try to call the fit functionality, VAE dot fit, which will actually start the training process. The first parameter will be the training data. Let's keep epoch as 6. Let's keep batch size as 64. Then what we have, shuffle as true. Then let's give some validation data. This validation data will be nothing but X test and X test. So here we are just trying to reconstruct images and not any classification or any other tasks, and that's why input and output will be X test and S test. Then callbacks equal to model checkpoint callback. Let's run this, and hopefully it runs without any error. Okay, there has to be a comma here. Model dot fit. Okay, validation. Here it should be validation data. Then we have another error, that is callbacks. Okay, this is some kind of typo error. Let's see where this is. Here. There shouldn't be any underscore. Okay, now we are in this first epoch. And T4 GPU is available. Again we are seeing one error. Okay, is instance. Again this is one typo error. Let's fix it here. If is instance. Now the training process is started. Now you can see that the training process is finished, like it's completed. 6 out of 6 epochs are completed. Initial reconstruction loss was 187.996, which reduced to 187.796. Similarly, we can see that with KL loss, initially it was 0.164, then the KL loss in the last epoch is about 0.0035. And same we can visualize it for validation loss as well. Now let's try to save this checkpoint. So save the trained checkpoints. So here we will save this VAE models and VAE. Then we will save encoder. We will use same folder, and then in that encoder we will also save decoder, models, and inside decoder. Let's run this. And as I'm using this Google Colab, it will be somewhere here. So in this models, I have VAE, encoder, and decoder. So this is our trained checkpoints, which we can use in like future use for inference. Now the main part, like let's try to reconstruct. So let's reconstruct using our trained variational autoencoder. For that, let's pick up how many number of images we want to predict. So number of images to predict, let's keep it a big number, let's say 5,000. Then let's select images from test data, let's say example images as X test. We will select 5,000 and labels. So these labels will be used to visualize the data, and they won't be interfering it with inference process. Okay, let's try to run this code. Now let's create autoencoder predictions and then display. So we have Z mean, we have Z logarithmic variance, we have this reconstruction or output from decoder, and we will use this VAE.predict functionality, and then example images as input. Then we'll run this, and the reconstructed images will be in this variable, that is reconstruction. So let's display it. So we already wrote this functionality to display images, so we will just use this function display images, and inside this we will give reconstruction or the predicted images. Let's run. Okay, so these are a few of the reconstructed images. Now let's visualize the latent space. Now you can see that these images won't make any sense because the number of epochs that we have trained this model is very less. So we have trained it only for 6 epochs. Actually it should be more than, let's say, 30 epoch or 20 epoch, more than 20 epoch at least. And that's why the total loss is higher, like 188.051 and 187. So there is not a significant reduction in the loss, and that's why the generated images are kind of blurry. So I'll try to increase the epochs in the next session, or you can try to increase this number of epochs. Now let's plot, or let's visualize the latent space. So we have Z min, we have Z variance, and finally Z, which equals to encoder dot predict. In this we will give example images, right? Now P is equal to the P values, norm dot diff, norm dot cdf, and then Z. That is cumulative distribution function. Cut it. Now let's select a figure size. Let's select 10. Then fig equal to plt dot figure, fig size equal to fig size into 2, comma fig size. Then we will add a axis, that is ax is equal to fig dot add underscore subplot 1 comma 2 comma 1. Then we will have plot 1. So we will plot two plots. First is the hidden first is the hidden space or the latent space, and second is of p values as well. So plot 1 is the scatter plot of z values, right? So z now 1, C map, let's say rainbow, and C equals example labels. So I have already told you that example labels will be used only for visualization and they won't interfere with inference. And then S equals to 3. Then plt dot color bar, and then plot 1, plot underscore 1. Now for plot 2, ax equal to fig dot add subplot 1 comma 2 comma 2. Then we have plot underscore 2 equal to, again we have scatter plot but of p values. So p comma p 1, again C map will be equal to rainbow, C will be equal to example labels, alpha will be equal to 0.8 and S will be equal to 3, and then plt dot show. Let's run this. we are getting this blank plot because we have got one error. So scatter is not defined. Here it should be ax dot scatter. Again we have got one error, that is it should be equal to. Sorry guys for this silly mistakes. Okay, now we've got this particular plot. Now we can see here that KL divergence term keeps Z mean and Z log variance close to standard normal distribution, and secondly, stochastic encoder leads to a more continuous latent space, reducing the occurrence of poorly formed images. Now if we run this for more and more epochs now, then we can see here clusters of similar clothes tied together, but they will be distributed across this 0 or across this mean as 0 from the origin. And finally, when we color code in this latent space by clothing type, we observe that there is no bias favoring any specific type. The right hand plot, this plot, the p-value plot, it displays the space converted into p-values, revealing nearly equal representations for each color. Now it is very important to emphasize that model learned clothing distinctions independently without using labels during training to minimize this reconstruction loss. So that's it guys for this particular implementation of variational autoencoders right from scratch in Python. So I'll upload this entire code to GitHub repository and you can refer to this code. And I'll try to output, and I'll try to also retain the output of this code by running it for more epochs. So that's it guys. We'll meet in the next session. Till that, if you have watched this video till now, do like this video and subscribe to the channel guys. Bye bye.